Okay, so we've learnt about support vector machines in their full generality. Let's see how it works, how they work on a simple example, which is the heart data, where we've got a bunch of variables, not too many, 10 or so variables, and there's two classes, heart disease or no heart disease, and we use the support vector machines to classify. So in these two panels, we show the performance on the training data, and next slide will show on the test data. So what we are showing are ROC curves. So we've seen these before, but just to remind you, once we fit our function, which is initially going to be a linear function, we threshold at 0, and that's a decision boundary. If the function's bigger than 0, we'll classify to one class, otherwise less than 0 to the other class. And you'll make a number of errors. You'll make some false positives and false negatives. Here we actually look at the false positives and the true positives. Well, as you change the threshold, you're going to change the false positives and true positives. And what the ROC curve does is trace out the true positives versus the false positives as you change the threshold. And that gives you a curve. And if you think about it, what you'd really like is a curve that really hugs this northwest corner. This one seems to be doing pretty well. Okay? And a way of comparing classifiers is to see which one gets closer to the corner. Okay? So that's called the ROC curve. The name comes from an engineering term, but it's not really relevant in terms of how we use it today.
And remember the so-called the AUC, the area under the curve, is the usual measure of how close the curve gets to the northwest corner. Right?
Oh, good point, yeah. Rob. So AUC, area under the curve, is a summary measure of how close you get to the corner here. If the area under the curve is 1, notice this is a unit cube, it means this curve exactly gets into the corner. And there's a 45-degree line. You should always be above the 45-degree line, so the AUC will be between 0.5 and 1. So in this left panel, we've got the linear support vector classifier, that's the red curve, and we're comparing it to linear discriminant analysis here, which is the blue curve. And on the training data, they do pretty much the same. Maybe the support vector's got a slight edge in a few places. Okay. In the left panel,
in the right panel.
Sorry, in the right panel, we compare the linear support vector classifier, which is the red curve, to the SVM using a radial kernel with different values of gamma. Right? And you'll notice that it's not monotone. So when gamma is 10 to the minus 1, we seem to do really well. When gamma is 10 to the minus 2, that's the green curve, we do worse than the red curve, and 10 to the minus 3, even worse again. So remember, the larger gamma, the more restrictive, the more wiggly the decision boundary. And so this is ordered in complexity. So when gamma is large, 10 to the minus 1, we're doing the best, and then as we decrease gamma, we start doing worse and worse. And the linear classifier sort of comes in between, in the middle of that regime. Which means gamma is another tuning parameter for the support vector classifier.
And just keep in mind, so what they're telling us, it's not really a fair comparison on the right panel, right? Because the gamma smaller has more complexity, so it's going to fit more. So and this is a bigger?
Yeah.
Yeah. So a training error comparison isn't a fair comparison.
Right. So we didn't do it here, but if we made gamma even much bigger, we'd probably get an area under the curve of 1.
Right.
So of course we know we should look at test data, and so here we put aside 80 observations as test observations and fit the classifiers on the training data, and now compared to now we look at ROC curves on the test data. And again, linear versus LDA, it looks like the support vector classifier does a little bit better, just by a small amount. Okay, but notice that this ROC curve is not as good as the previous one on the training data, because that was overfitting a bit. And in the right-hand panel, we look at the different support vector machines again, and now the one with the biggest value of gamma actually does the worst. So while it was doing the best on the training data, it actually does the worst on the test data. And here the linear support vector machine does pretty much the best, and the most regularized SVM is with gamma 10 to the minus, can't see that number, but 3, is doing about the same. Okay, so these are tuning parameters, and we'd have to use all our usual tools for deciding if we had to pick a value for gamma, we may use cross-validation or validation data set to pick it. As well as the cost parameter C. So with a kernel, we've got 2 tuning parameters. With a linear support vector classifier, we've just got 1, which is C. Okay, so everything we've talked about so far is for 2 classes, separating hyperplane 2 classes. So what do we do if we have more than 2 classes? Well, unfortunately, things get a little bit ad hoc here. And so there's 2 general approaches. And the one's called OVA, one versus all. It's an acronym. And so the idea is you fit k different 2-class support vector machine classifiers. Each class versus the rest. So you just relabel all the other classes as a mega -1 class and say the target class as class +1. You fit a support vector classifier. And you do that with each of the classes as being the +1 and all the others being the -1. So that means you'll fit k different classifiers, which means you'll have k different functions. And now when you come to classify a new point, you evaluate those k different functions, and you'll classify to the class which is the largest. So that's the one approach. And the other approach is OVO, which is 1 versus 1, which means you do all k choose 2 pairwise classifiers. So if k is, for example, 10, that means you have to fit k choose 2, which is
45.
45 classifiers, right? And so obviously that gets big as the number of classes gets big. And so now you've got all these pairwise classifiers, and to classify a new point, what you do is you evaluate every single one of these classifiers, and you see which class wins the most pairwise competitions. And that's the class to which you classify. So these seem ad hoc. The actual mechanisms aren't quite as ad hoc as they sound, and so you can explain this from a somewhat theoretical point of view, but that's what gets done in practice, one of these 2. If the number of classes is too large, usually OVA, otherwise OVO tends to get favored. Okay, we're near the end of this section. We'll end up by comparing support vector machines to logistic regression. So remember, logistic regression did solve classification problems by modeling the probabilities of the classes, where support vector machines were optimizing, going directly for the decision boundary. They seem very different. Well, it turns out they're not as different as one might think. So if we write the linear function in this form, as we've done before, it turns out we can rephrase the optimization problem for the support vector classifier in the following form. Now, this is somewhat technical, but there's a loss function between y and f of x, summed over the observations. So this is similar to, but not the same as, a log likelihood. And there's a penalty on the coefficients. It looks like it's a quadratic penalty, like a ridge penalty here. And there's a tuning parameter lambda. Now, this loss function is a somewhat strange beast. It's known as the hinge loss. And maybe it's better just to show you a picture. So its primary argument is y times f of x. Remember, this is what we call now the margin. This is the quantity we'd like to be positive. And the bigger it is, the further a point is away from its margin. Okay. So this is the loss that we assign to that quantity. In this formulation, if it's bigger than 1, we assign 0 loss. So that's 0 over here. But if it's less than 1, and particularly if it goes negative, it means in all these regimes we're on the wrong side of our margin, we pay an increasing linear loss. So that's called the hinge loss. And if you optimize this problem, this criterion with respect to the betas, the solution is equivalent to the support vector machine.
Well, that's not obvious, right? It's pretty hard. The derivation is not so easy.
Really, Rob? You can't see just from looking? No, it's very hard. Well, it's not very hard, but it's quite hard to map this to the other one. But what's more important, and it's not necessarily that this is the way one does it, it's just illustrative because it allows us to compare to logistic regression. Of course, with logistic regression, we also fit in a linear function, so the function looks the same. Remember there, the linear function was the logit of the probability of class 1 versus class -1 in this case. So, and for logistic regression, we had a log likelihood plus, we could have a log likelihood plus a ridge penalty. And the log likelihood is given by this green curve over here. And you'll notice it looks very similar. In this formulation, it tapers off to be horizontal over here. It asymptotes to be linear over here. But instead of having the sharp corner over here, it has a gentler corner. Which means you can also think of logistic regression as having a kind of soft margin and that it focuses more on points close to the margin than points further away. So there's a lot of similarity between logistic regression and support vector machines. And if you want to learn more about that, you may want to look at our book, Elements of Statistical Learning, where we go into this in a little bit more detail.
There's one thing to add. The fact that the hinge loss has that corner is what gives it the support vector property, right? There's the alphas that are, some of which are 0, whereas the smooth loss doesn't have that property. You don't get support points.
Good point, Rob. And you may get points whose sort of weight gets close to 0, but not exactly 0. Okay, so which to use, support vector machine or logistic regression? We'll just sum up here. So if the classes are nearly separable, the support vector machine tends to do better than logistic regression. And so does linear discriminant analysis. Logistic regression actually breaks down if the classes are exactly separable. In that case, you'd have to use some kind of regularization with logistic regression. But that's a regime where support vector machines do well. When the classes aren't separable, where there's quite a bit of overlap, logistic regression, perhaps with a ridge penalty or with a lasso penalty, tends to do better and is more useful. They're similar, the results will be similar, but it's more useful because it's actually estimating probabilities for you. For nonlinear boundaries, you can use kernel support vector machines, and they're popular. You can use the same kernels with logistic regression and LDA as well, but the computations tend to be more expensive. And so in those scenarios, support vector machines tend to be used. So here we are at the end of the session. Rob, do you have anything to add here?
Well, I was going to add about, there's sort of a no free lunch principle. With support vector machines, we saw a way with kernels to finesse to get a solution essentially in high dimensions for free. But the one price you pay is you don't get a feature selection like you get for the lasso for L1 penalties, right? Where we explicitly put a penalty on the features, and as a result, a lot of the features are set to 0. With support vector machines, one disadvantage is it uses all the features and it doesn't easily select which features are important. So for high dimensional problems, that can be a drawback, not so much for the classification performance, but for the interpretation of the solution. And the other point that Trevor mentioned about probabilities, that's a really important point. Like if you're working on a cancer diagnosis problem, very often you don't just want to classify, but you want to know the probabilities of the estimated class probabilities. Because if something's got a probability being cancer of 0.51 as opposed to 0.99, the classification is the same, but the implications in the actual situation are very different. So class probabilities are very important, and support vector machines don't provide an easy way of getting those.
The community in support vector machines have tried to address these problems with sort of post ad hoc kind of add-ons, something called recursive feature elimination, and also they have ways of actually getting probabilities by fitting logistic regressions after fitting support vector machines. But we can do that directly with for example, lasso regularized logistic regression.